Hi ladies and gentlemen, this is Mr. Green and this is another in my pre-cal lessons so that you can learn how to do these things. We're dealing with trigonometry, oh boy, oh joy, and where we're at in this whole process is that we're looking at graphing polar coordinates and doing graphing of polar equations. Now the whole first part of that unit, that lesson, is making certain that you're familiar enough with polar coordinates and with polar graphing that you'll be able to do some of it. One of your best friends at this point is going to be your calculator. I want to make certain you all know how to turn this calculator into a polar graphing device for you. First thing you do is you press the mode button, and then right here you can see I've got it in degrees and I've got it in polar coordinates, and all you got to do is arrow down to those things over here and make certain it says degrees, and then you arrow down to the one here, and it normally is on function, but I took it over here to polar. That's for polar coordinates. And then when you save this, your whole y equals becomes r equals. Haha, that's how we can tell them apart. Now, some things about the window. It helps to have your window set up so that you can see a bunch of rotations if you need to. I've got my theta set at 1440 because I want it to go around 4 times. Okay, I want to see 4 revolutions of it. And then when I zoom it, a lot of times what I'm going to have to do is hit zoom and go to zoom 0. Okay, well, zoom 0 stands for fit. Okay, so here zoom fit. If I do that zoom 0, it sometimes makes it fit on there a little bit nicer. Okay, so I'm going to move my, I don't want to make it that big. Don't want to make it that big. Thank you. I want it to just get a little bit bigger. Okay. Well, looks like I'm not going to get it to move over there where I want it to, so I'm going to move it over this way a little bit so I can see what I'm doing. Okay. You can't see my bottom row's numbers there, but that's okay. You'll be able to figure out what's going on. Okay. So let's move on to the next slide here, if I can get to where I can actually see my move on to the next slide. There it goes. Okay, the second part of this lesson deals with some graphing families. And just like over in regular coordinates, we had the linear graphs, we had the quadratic graphs, and we had the to the third degree graphs and things like that. And we learned how to recognize those just by looking at their shapes. Same thing's going on here in polar graphing. We're going to look at some of the different polar graphing families. And the first one we're going to look at is just the rows. Now the rows is either r is equal to a sine n theta or r is equal to a cosine n theta. It won't matter which one you're using there. Where a is greater than 0. If you have an n is an even number, this n right in here is an even number, pen, solar pen or something, pointer so I can show you what I'm talking about. That n right there is an even number, then you're going to get an n times 2 number of petals on your flower, on your rose. If it's an odd number, it's just going to give you that n number of petals. Okay? So let's try it on our calculator. Okay? So what are we going to do? We're going to press y equals. We're going to say 5 times cosine 3 theta, and hit enter. And I'm expecting to get 3 petals on there, each one of them of size 5. So when I graph this, I got 3 petals on there, each one of them size 5. Okay? So let's try a couple more here, see what we get. Let's leave that 5 there, but let's change this to, say, 4 theta. Okay? Cooperate with me here, calculator. Thank you. 4 theta. When we say 4 theta, we're expecting to get 8 petals on here. So let's look and see what we get when we do this. Well, I got 8 petals. 1, 2, let's count them with me. 1, 2, 3, 4, 5, 6, 7, 8. 8 petals. Wow. Seem to fit just beautifully. And if I do a zoom fit again here, it will make certain it all fits on the screen. Cool? Now, what if we change that A up there in front? What if we change that to a 2 and graph it? Does it look a little different? I just got a little bit smaller, didn't I? I can now zoom it up again, zoom fit, and it's going to fit in there just fine. Cool? Cool. Okay. That's what the rows is going to look like. Okay? So let's go on and look at the next family member here. The next one is called a cardioids. Cardioids. This one is of the format a plus sine theta or a plus a cosine theta. Okay, and it's either plus or minus. It depends upon which way it's going to go around the circle. That's what it's going to amount to. But a is going to have to be greater than 0. I want you to notice there's an a here and an a here. It's the same value in both places. This one looks like a heart, and that's the Greek origin of the word for this cardioids. Okay, this is the one that microphones are based off. So this is the one that gets used a lot in sound engineering when they're doing some sound engineering work. So let's try a couple of these, see what they look like. Okay, so we're going over here to y equals. We're going to say 3 minus sine. I'm sorry, 3 minus 3 sine theta, and hit graph on this. And we're going to do a zoom 0 to make it fit on the screen. And it looks like that. It does. It looks kind of like a heart, doesn't it? Okay? Now I want you to notice that from here, from this point here to this point down here, should be about 6 units. Thank you. 1, 2, 3, 4, 5, 6. 6 units from the origin down. That's where we got to here. Cool. Does that make sense how I'm getting that? Let's try another one. Make it a little smaller. Okay. So let's say here 2 minus 2 cosine theta. And hit enter. And hit graph. And it goes up the other way, and so I'm going to have to zoom fit again just to make sure it all fits on the screen. And it'll look like, it does, it looks like a heart. That's what we're looking for in that type of a graph. Very obviously you can tell that different from the one that we were looking at with the rows, right? Okay, let's move on and look at the next one in the family. The next one in the family is called a lemicon. A lemicon is another word for a snail. It's a Greek word for a snail. And I'm not real good with Greek, so I'm not real good at this one, okay? I want you to notice it looks just like the one that we were just looking at, doesn't it? A plus or minus A sine theta and A plus or minus B sine theta. They're very much the same, except that B and A are not the same values any longer. And we're going to use that A is greater than B, and that'll help us on our calculators to make certain that we're looking at the right ones, okay? So let's look at one here. So let's say we've got a 6 minus 2 cosine theta. Let's do a graph of that one. And we'll have to zoom it to make certain it fits. Zoom fit. And we should get... That looks almost like a circle, doesn't it? Let's see here. A, B, yep, I'm doing it right. 6 minus 6 is the A, right? Yeah, 6 plus or minus 2 cosine. Oh, I'm doing cosine. That's why it was looking kind of weird there. Why it was on the wrong side of the graph for me, anyway. Let's do a sine theta there. Okay, and instead of a minus, let's make that a plus, just to give us something different. Graph, zoom 0. Yeah, it looks like that. These are looking an awful lot like a circle, aren't they? Let's see, let's go back to our window here and bring this back down to 360 degrees, because I have a feeling that's probably one of our problems. Okay? And it's just through experience that I know what these window values should be. 7.5, See if that doesn't clear it up a little bit. Zoom, fit. Yeah, looks like a circle. A little bit higher up, right? This is one that you ought to try on your calculator. Make certain you know what it looks like. Okay? Okay? So let's look at the next one here. After a lamacon is a lemescadates. This is the one that's supposed to look like a ribbon. Okay? I want you to notice I've got r squared terms here. So what we're going to be dealing with when we're trying to put it in terms of r is dealing with square roots. Okay? So what are we going to be we're going to be looking at, let's see here, trying to graph some of these, make them look like ribbons. Okay, this is the one where I got to think just a little bit. So let's leave it at 6, just because we want to leave it there. 6 squared. Okay, so you're not wanting to cooperate with me, calculator. Is that the deal? Yep, my calculator just froze up on me here. Okay, that's nice of it. Well, you know what? That's why I have more than one calculator available to me. Let's see here. Sometimes the calculators just don't want to be nice to you. And when that happens, you clear the calculator and you start off with all over again. Okay? Well, I cleared the calculator completely. I'm going to go back into mode. I'm going to make certain that this one is set in degrees. Thank you. And in polar coordinates. Okay? And I'm going to go into y equals. And I'm going to say 6 squared. Okay? Make certain I know what I'm talking about here. I'm going to do 6 squared sine 2 theta parenthesis, and I'm going to hit graph. Oops, you know what I forgot there? I even said it. It's a square root function. So I'm going to insert a square root symbol here. Like I said, I had to think about it. Once my calculator died, I didn't think about it. And then I'm also going to put a second square root of 6 squared sine 2 theta parenthesis. Okay, enter. And I'm going to hit graph on this. Hopefully it's going to look like a ribbon. Up, zoom 0, fit. Window. Okay, we want it to go to 360 degrees. Enter. Graph. Zoom. It's thinking. See the little arrow going up and down over here? It's thinking a lot. This one doesn't work quite as fast as the other one does. But it's working right at the moment. That's what counts. Uh-huh. It is working. And zoom 0 to make it fit. Yeah, 0 for fit. And it's going to take it a while to come up here again because this is running just super fast. But it should change the graph a little bit, and we should see something that looks a little bit like a ribbon. Hang on with me. I am telling you to try these on your own calculator. Make certain you know what they look like. Okay? The reasoning why we're doing these and why I'm bringing up these different families is because what we're going to be looking at is if we can figure out what type of a graph it is, a rose, a snail, a heart, or a ribbon, it tells us what the equation looks like, right? And if we know what the equation looks like, yeah, see, it's beginning to look more like a ribbon there. There it goes. Now I got my ribbon. See how it's got two different lobes on it here? Looks like a bow, doesn't it? That's what we're talking about. Cool? If we can figure out what it looks like, then what we can do is we can relate that back to one of the equations. And it helps us knowing what we're looking at to help us know what the equation is going to look like at the end. Okay? And that's where we're getting these from on these family of graphs. Okay? It's kind of like if we knew that it was going to be a parabola, all we had to do is put in the formula for a parabola and see which one it was and make it work, right? Well, in the first part of this lesson, they do talk about how to draw straight lines and how to draw circles and how to draw all sorts of different things and how to draw the different conics. Remember the conics, the hyperbola and the parabola and the ellipse and the circle? You get to figure out how to draw each one of those. That's where this polar coordinate stuff actually came from and where it's used from. But the main thing that comes up, and it's the hardest topic in this entire lesson, is right there at the end. It talks about symmetry. Now, polar graphs have four types of symmetry. They've got a symmetry across the polar axis, they've got symmetry across the y-axis, and they've got symmetry across the pole. Now, let's just look at this one that we just graphed here. And it went off. Come on, turn back on. Thank you. You see, the pole is this point right here at the very center. Okay? And when we're talking about symmetry about the pole, what we're talking about is through the origin right here. Okay? There is a way of doing this one, and what you have to do is you have to, well, I have to move everything down just a little bit here. You have to, come on, work with me, thank you. What you have to do if you're looking about going about the pole is you replace r and theta with r and negative theta or with negative r and pi minus theta. And if you get the same thing, then it's got symmetry about the polar axis. That's the one that runs through the center there. Okay? If you're talking about going over about the y-axis, that's where theta is equal to pi over 2. And you can replace r and theta with r and negative theta or with r and pi minus theta, either one of those two. And if it gives you the same thing, then what you're looking at is something that has symmetry about the y-axis. If you're talking about, I said that backwards a while ago. I said polar axis is this last one down here. The polar axis is actually the, what we used to call, I'm sorry, is this one right here. This is the polar axis going across like this. The pole is this thing right here in the middle. The polar axis is this one going this way. The y-axis is going this way. So I'm sorry if I just confused you. If I'm looking for the polar axis, I'm looking for this one here. The one we're looking at on the screen there does not have symmetry across the polar axis. It has symmetry across the pole, this origin point right down there. Okay, and that's the one where we're looking at down here. Okay, across the pole. And what you would do there is you would replace r and theta with negative r and theta or r and theta plus pi. If you're looking at something that's going to have symmetry across this y-axis going up and down here, what you're looking to do there is replace r and theta with negative r and negative theta. This one does not have symmetry that way. I can't replace that, the r's there, the r with a negative r and have it come up with the same theta. Okay? So remember, four different types of symmetry. There is a way of doing it here. If you can look at the graph and see what it's going to be, like in this particular case, You look at this one, you can see the lobe is up here and the lobe down here. It's got to be only this one here. It can't be over the x-axis and it can't be over the y-axis. So it's got to be just over the pole here. It's kind of like a reflection, or I'm sorry, a rotation of it, isn't it? So that would be the one that you would say is over the pole. Okay? And that calculator's dead. Okay. So what we need to do is, if we can look at them, great. If we can't, then what we have to do is we have to substitute values in. So let's go back and look at some of these real quickly. If we're looking at the one here that's the rows, well, you know what? Rows, you can usually get them to be across the y-axis, and sometimes you can also see them across the x-axis. It depends upon how many petals they've got. So if they've got an even number of petals, sometimes you can do it over the x-axis, or the pole, not over the pole, over the uh, wow, words, the polar axis. Okay, so roses, if they've got an even n petals, they are symmetrical across the polar axis. You can say that they are symmetrical if they have an n number of petals across the pole as well. And a lot of times they're symmetrical across the y-axis. If there's an odd number of petals on it, then a lot of times the only ones you're looking at are the y-axis and the pole, but not even the pole. No, I'm sorry, just the y-axis is the only one you'd be able to look at there. Yeah. Okay. So if you're looking at cartids, these are going to be ones that you're going to be able to look at it and say, it depends upon what we're doing, either plus or minus here, and whether it's sine or cosine, but you're going to be able to figure out it's either across the y-axis or across the polar axis. One or the other is where you're going to be able to fold that and find that line of symmetry. If you're talking about a Lachmann here, those are the ones that most of these are only got around the pole, as far as what we can look at as far as symmetry is concerned. Very rarely do they have the other two. Okay, these are the ones that we can look at here as the ribbons, and these ribbons are the ones that have pole symmetry as well. Very rarely do they have y or x, polar axis or y symmetry. Okay, in case you don't know, it's hard to convert between polar and regular geometry. And once you get into it, though, it's really, really fun, and you can have some fun with it. These are the ones that you can draw some really cute figures with. Okay, so secret word for today, I'm going to leave it at walk. So if you watch this video, please send me a text, or a K-mail saying that you watched the video. I do appreciate the fact that you guys have been real good about telling me that you're in pre-cal when you send me K-mails. It really does help me find your information quickly. I will talk to you later.